let me write the Stokes theorem again. Whatever the vector field you have, okay, open surface integral, am I right? Stokes theorem. So what is other name? Fundamental theorem of curves, isn't it? Just like fundamental theorem in calculus, okay? Just like any other fundamental theorem, okay? So open surface integral of curl of any vector field, okay? Any vector field, okay? Dot dA vector. Open surface integral of curl of any vector field dot dA vector. So that's equal to closed path integral of, okay, that vector field around a closed loop. Now the question is, okay, I mean, if you have grabbed the logic, whatever I explained in the last class, this is not necessary, okay? I mean, this whole discussion is not necessary. But still, I mean, you may not remember that one for a long time, right? That's only for time's sake. For a long time, whenever you see this relation, you should be able to know what is this surface, what is this path, what is this dA vector, what is the direction of dA vector, okay? Just whenever you write the Stokes theorem, okay, later, while applying, you should be able to quickly grab what is the path, what is the possible surface, what is the dl vector, what is the relation between this dl vector and dA vector and all, okay? That you need to grab, okay? So that's a sign convention. You take it as a sign convention. It's not a sign convention. It all came from what you call your circulation definition, okay? Your curl and its relation to circulation, whatever you have written. So from that definition, these things arise actually, okay? So again, recall whatever the last discussion that I have done, okay? Adding all circulation, you will get total path integral, am I right? That's the basic idea. Adding all circulation, so throughout the surface, it will get a total path integral, am I right? So if you take that one, you have already fixed what is the direction of dA vector. You already, again, you have started with the surface area only, isn't it? You started with the surface area there, okay? But sometimes what we do is we start from here, okay? Then we need to define the surface, okay? Sometimes we need to define the surface first, then we need to define the path. Two things are there, okay? Sometimes this path is well defined, later you define the surface. That is the most usual thing, okay? You will have a path actually, later you need to define the surface. That's the most usual thing that appears in the application. But what I have done is I have taken the surface initially, am I right? Then I defined what is this path. This path is a boundary line of the surface, isn't it? Just like the best example is hemispherical bowl, isn't it? Hemispherical bowl, can you imagine? Is that okay? Hemispherical bowl. Now again, this is an open surface, am I right? This is an open surface. Now look at here. If suppose this is the surface, if suppose this is the surface, what is the path? That path I told, that path is the boundary line of the surface, am I right? If you go, what is the boundary line of the surface? I mean, if you go here, again your surface will end here, am I right? These are the end point of the surface, can I say like this, these things? So that is a circle, am I right? End point of the surface is a circle, isn't it? So check this out. So that's why if this is the surface, okay, so this is the boundary line. Is that okay? So this is the boundary line of the surface. Now how to fix this, what you call, this path integral, whether clockwise or anti-clockwise, this surface integral, which dA vector you choose, because whenever you get open surface, you got two dA vector direction, am I right? Now look at it, that is fixed by again right hand thumb rule. That's what we did in case of circulation definition also, am I right? Curl and circulation definition also, we did the same thing, okay? Now look at here. If you take your what you call path integral, again, so let me start with here, okay? Let me start with this one. So if you take your dA vector like this, if you take your dA vector like this, is that okay? So then again your thumb, again in the right hand thumb rule, your thumb should represent the dA vector direction, but again that is comfortable only for planar area. It's a curved area, okay? It's not so comfortable to apply, but still look at here. If this is the dA vector direction, okay, if my thumb is a dA vector so direction, my fingers, 4 fingers should represent the path integral direction. Now I have taken dA vector direction. Now you can argue dA vector is not only like this, it is like this, like this, like this, isn't it? But so take it like this, okay? This is the dA vector so direction. Your fingers will represent the direction of the path integral. Is that okay? Or if you take the same thing, if you take the same hemispherical ball, okay? Now wait a second. So if I take this dA vector in, actually there is no inward and outward for this what you call open surface, okay? But since it's a hemisphere, we may say that it is inward, it is outward. This looks like outward, isn't it? There is nothing like inward and outward for open surface actually, but still, look at here. If I take what you call my area vector like this, okay, dA vector. So that's another choice for open surface, am I right? Area vector. So can you hear me on Google Meet? Speak out. That's another choice of area vector, isn't it? So then again use right hand thumb rule. Your area vector is like this, am I right? Your area vector is like this. Again, you can use your right hand thumb rule. Your finger should represent the direction of the line integral. I mean this is the what you call boundary line of the surface. Okay, this is the boundary line of the surface, and this is the direction of the line integral. Is that okay? So this is the path, this is the surface, this is the path, this is the surface. Is that okay? Check this out. Can you grab this idea? Actually, if you take the earlier logic, again, actually this is obvious fact actually. For individual circulation, you have taken what you call like this, okay? Those will add up and it will become total circulation like this. Here I think you have taken individual circulation like this. Small circulation. You have added, am I right? So that total circulation happened to be like this. That's how it happened actually. It's all because of individual circulation you have chosen. Okay, small circulation or curl. That's the curl definition actually. Is that okay? So now again, sometimes again what you do is you define a path. Okay, you define a path. Suppose let me define a path like this. Is that okay? Which is a circle, centered somewhere here. Is that okay? Let me take this one as xy, xyz. That's more comfortable. Is that okay? Circle is on xy plane. Okay. Now again you start with here. You have taken line integral here. Is that okay? Now look at here. So see this expression properly. I think I did interpret already. Okay. Now this is very similar to, look at here, a to b. df by dx into dx is equal to f at b minus f at a. Is that okay? So integral of some derivative that is given by value of the function at end point. Here that's a vector field actually. That function whatever I'm talking about, that's a vector field here. Is that okay? So I hope you can find the similarity. So between Gauss theorem, Stokes theorem, and fundamental theorem of gradient and all, and this what you call our single variable calculus theorem. Okay. So now look at here. So there are infinitely many surfaces whose boundary is this path. Am I right? Or for a given boundary, for a given path, okay, I can define infinitely many surfaces whose boundary is this path. Isn't it? What is the simplest surface? This plane itself. Plane itself is the simplest surface. If you start with what you call path integral, if you want to go for surface integral, you take a simplest surface. Why do you make it complex? Why do you make this part complex? This is how we think when we apply that one. And when you, so what you call, I think in the example problem he proved like that only. Is that okay? You have a circle in xy plane, okay, and that is a path integral, okay, this part of the theorem, okay. What is the surface you can choose? You can choose, there are infinitely many surfaces whose boundary line is this path, okay, and that plane itself is one of the surface, and you can take again hemisphere, isn't it? or you can take any weird kind of surface, balloon kind of surface, isn't it? That's your choice. But the convention is, if path integral runs like this, okay, your dA vector should run like this, isn't it? Here, suppose if you take hemispherical surface, okay, your dA vector should run like this. That's the logic. Is that okay? And one more thing you need to observe, okay? So since this is equal, am I right? So this depends only on the boundary line. It is independent of the surface chosen for a given bound. I think I have given that statement. Speak out, anyone? I have given that statement. Speak out. So I have given the statement or not? This is path integral, this surface integral is independent of the surface. It depends only on the boundary line like that. Speak out, someone. Can you hear me?
Yes, sir.
Yeah. So just note down that one, okay? So those are two observations that we can make whenever we observe that one. So right hand side depends only on the path. Okay, that's why there are infinitely many surfaces that you can choose, because equality is valid always, isn't it? So that's why again, this surface integral is independent of the surface for a given boundary line of the surface. So that's the statement. Now what I do is, okay, yeah, so that's the one thing. Okay, now look at here. Yeah, speak out.
Sir, here in these figures of the hemisphere, the area vector outward or inward?
No.
That it is anti-clockwise direction or?
Yeah, but look at here. Don't fix it like this, okay? Don't fix it like inward or outward, because for open surface there is nothing like inward and outward, okay? Here how I did fix this dA vector, I have taken my fingers along the path integral direction, thumb along dA vector. For planar you can do, am I right? For planar you can comfortably apply right and thumb rule. But the problem with the curved surface, am I right? Now again apply the same logic here, okay? Your fingers represent the dA vector direction, like that, just move on, okay? Now your dA vector directions here. Is that okay? Speak out. But there is nothing inward and outward, okay? Because if you have that idea, later you may get into trouble. For open surface, there is nothing like inward and outward. I mean, here it looks like that, okay? Don't remember it like inward and outward. Again, fix it by right and thumb rule only. Is that okay? Speak out. Or start with your circulation idea, small circulation, and just think all of those circulation add up to give total circulation at the end, isn't it? So think like that also. Again, last class, so interpretation. That's also okay. But again, what I'm thinking is, whenever you see this one, you should be able to quickly fix the dA vector and dL vector direction. Okay, they have the relations. Okay, if you reverse that one, the dA vector should be reversed. Is that okay? Yeah, speak out. Speak out. Don't think like inward and outward for open surface. Okay, even though it looks like it will create a volume inward and outward, don't do that one. Okay, you may be in trouble later. Speak out. So let me take one more idea. I have a pot, suppose, okay? I have a pot, suppose. Is that okay? Again, I can write this direction, okay? So this is like this, isn't it? Now your dA vector will be like this. Once you choose this dA vector like this, okay, look at here. Everywhere you have to choose dA vector like this. Now you can ask, what happened to your right hand thumb rule here? Isn't it? But I hope you can fix that one. Is that okay? Don't take dA vector outside, okay? dA vector, once you choose, everywhere you have to sweep like this. Is that okay? Speak out. I think you better start from circulation only. That's a pure idea.
Sir, all the dA vector adds up to give the line integral.
Yeah, you better to think like that last class interpretation. These all circulations adds up to get total circulation. Okay, so that each of the circulations were actually this dot product, and you have integrated. That's the equality. That's the best way to think of that one. Okay. So this is the dA vector direction. Is that okay? If you reverse the direction, you have to reverse the dA vector. Are you getting my point? So don't take dA vector like this because my right hand thumb rule says like this. Is that okay? No, not like that. Okay. Or you do one thing. You just shrink it to a plane. If the surface you have taken, this surface you have taken was a plane. Okay. So then you would have chosen dA vector like this. Am I right? Okay. Just take it as a rubber, and now what you call? I'm making it as a pot.
Sir,
Huh?
what's the initial point? It is the planar surface and
No, those are all choice.
Okay.
Any surface you can choose. But while applying, again, we choose the simplest surface, planar surface. But you should know that one, isn't it? For
You can choose
any shaped surface. But if we want to do this one, then why would you choose the difficult surface? You choose the simplest surface linked with this path, isn't it? That's the rule. Are you getting my point? You do like this, okay? So you just think it as a rubber. Again, first fix the direction of dA vectors for a plane, then just dig into that one. Then what will happen? This dA vectors will happen like this because. Speak out.
Sir, dl vector always should be the perpendicular to the surface. That's why we
dA vector, yeah.
dA vector, yes, sir. So,
Yeah. So it is no. What I'm saying is, so perpendicular to the surface, there are two perpendiculars to the surface everywhere. Am I right? So that's what I'm saying. So these are these are like this actually. Because so if it is a planar surface, dA vector like this. Am I right? Suppose if you just shrink all of this to plane, your dA vector will be like this. Check this out. Imagine like that. Or you have started with this one. It's a rubber. Okay. So just you made it as a pot. Then dA vector will be like this. Check that out. That's how you need to fix. So don't take one dA vector like this here, other dA vector like this here. No. Look at here. This is one side of the surface. These are the one side of the surface. Am I right? These are the one side of the surface. These are the other side of the surface. Can you imagine? There are two sides for that open surface. So carefully handle that one. Okay. Yeah. You need to solve problem. That's it. Okay. There is nothing. So like that. Suppose if I have an egg. Okay. And I'm breaking the egg. Then when you break the egg, something like this will happen, isn't it? Isn't it? So can you just imagine this one? Is that okay? You broke an egg, okay? It has broken like this, okay? So this is an open surface now. Now let me start with the surface. What is the boundary? Boundary is this one. Boundary line of any open surface is a closed loop. Isn't it? This is a boundary line now. Speak out. That okay? Whatever the open surface you take, its boundary. Boundary means end point of the surface. Okay? These are the end part of the surface. That's that's a one closed loop actually. Yeah. Again, now here also you can use your right hand thumb rule to fix the dl vector and dA vector direction. Okay? Now look at here. If I shrink this path to 0, then surface becomes closed surface, path integral becomes 0, right hand side becomes 0. Is that okay? Then surface becomes closed surface. Can you imagine that one? If I shrink this path to 0, okay? Suppose if you have a balloon, okay? Suppose if you have a balloon like this, okay? So you are just blowing that one, okay? Then what you do? You are going to tie that one, am I right? You are going to tie that one here. Then it will become a closed surface, am I right? Once that becomes a closed surface, so this, when that path integral shrinks out, this part is 0, isn't it? This part will become closed surface. So since again right hand side is 0, so closed surface integral, whatever the closed surface integral you take, okay, whatever the vector field you take, this is general for general vector field, okay, curl of a vector field, curl of any vector field is a special class of vector field, dot dA vector, so that's equal to 0. Okay, two things you can observe. One is This is independent of the surface for a given path, and close the surface integral of a curl of a vector field is 0. Is that okay? This will happen for magnetic field actually. Is that okay? These things will happen for magnetic field.
Sir, what you said, curl of a closed surface will be 0.
Curl of any vector field, okay, if you take a surface integral, closure surface, curl of any vector field is again vector field. If you take a closure surface integral of curl of vector field,
then it will be null vector.
no, after taking dot product, yeah. Inside the integral, we didn't put any what you call vector actually, isn't it? In any of these three theorems, somehow dot product came, isn't it? Or scalar came in case of divergence, isn't it? Gauss divergence theorem, okay?
Sir,
yeah, yes.
What is the example of that one, sir? What is the example of that?
Magnetic field will behave like this. Magnetic field, what you call this whole thing you can write it as a magnetic field. This one you can write as a vector potential. We shall see that one later. Magnetic field, what you call? No, wait a second. Magnetic field only. Magnetic field only. It's a special class of vector field. Okay, so which is so this will be A then. Okay, whose surface integral is independent of the surface chosen. Okay, that's why we write magnetic field as a curl of some other vector field from this theorem. Okay, we shall see that one. Okay, I mean in this chapter he defined whatever the theorem required for whole electrodynamics. Okay, I think I need 2 more classes to discuss that one. Okay, one class is to discuss coordinate part. Okay, so a spherical and cylindrical coordinate, all of this expression in that one. And other class is to what you call list out all theorem, all possible theorems. Okay, now let me quickly list out kind of what you call integration by parts kind of idea in case of these 3-dimensional integrals, so that in the evening I can go for next topic, isn't it? So just let me what you call give these couple of theorems here. Okay, so del dot, okay, F into A. F is scalar field, A is vector field. Is that okay? So that's equal to, do you remember? F scalar field into del dot A minus or plus? Plus A dot gradient of this scalar field. Is that okay? Now you can have an integral of that one. Take an integral of this one, volume integral. Volume integral of del dot Fa. Is that okay? D tau. Is that okay? Speak out. Now that can be written as, actually I think this is going to be used, okay, somewhere. That can be written as closure surface integral of, where surface is a boundary of this volume. Surface is a boundary of this volume of F into A vector dot dA vector. F into, isn't it? That's how we write Gauss theorem, or what you call fundamental theorem of divergence, isn't it? And that can be written as, again you can just do this one, isn't it? Volume integral. Scalar, do the volume integral. Okay, so that's equal to volume integral of F into del dot A, okay, d tau, the same volume. Okay, I hope you know the relation between this volume and this surface I have written. Okay, plus integral of volume integral of A dot del F, okay, d tau. Now from this expression, I think he will solve it for F del dot A d tau. He will solve it for this one. Is that okay? This whole equation, he will solve it for this one. And that may be required somewhere, okay? Volume integral of, okay, F del dot A. Yeah, any question? Somebody typed in chat? D tau. D tau, that's equal to So closed surface integral of, okay, this will become minus sign, am I right? If you take it this side, he has written like this, minus volume integral of, okay, volume integral of A dot del F, okay, A dot del F into d2 plus closed surface integral of F A vector, okay, dot dA vector. This is what you may need to remember, okay. I mean, don't by heart or something. I mean, whenever we need that one, we shall look back into this expression. I don't think that's required for exam, but it's required for understanding some part of the theory. I think in this was there, this expression, okay. No, I mean, we use this one in the derivation center. I mean, I think that's a derivation of, I think, something related to pointing theorem, okay. This will come actually, we shall see that one. Yeah, still one more big assignment you need to solve. Okay, I think you have solved problems relating to Dirac delta. Anyone? I did share some notes and small, isn't it, during quantum mechanics. Oh yeah, that is required here. Okay, some Dirac delta problems are also there in this chapter. Also, you solve them. Okay, some properties of Dirac delta, and from I think I might have shared some link from Wolfram Math. Okay, there you may need to release it, or I shared some PDF files. Okay, or let me share it again. You need to work on Dirac delta also, okay, by evening, so that I will skip the Dirac delta property part and I will directly go for that 3-dimensional Dirac delta and the requirement of that one to fix one ambiguity here. Okay, so what will happen is, again, our Gauss divergence theorem looks like it is not valid for one situation for a point charge. But it's not like that. Our derivative, will not exist for that kind of situation. These things are true only when this derivative exists. I mean, whatever the theorem you have written, those things are true when you can take the derivative of that function or something, isn't it? When you can't take the derivative, you can't expect that one to be valid. And we are going to fix that one by Dirac delta for a point charge situation. Okay, for a point source situation. Okay. We shall see that one. That's also important part. Then some theory of vectors.